Distance of closest approach between the two ships. Two ships are 10 km apart on a line running south to north. The one farther north is streaming west at 20 km per hour. The other is streaming north at 20 km per hour. What is their distance of closest approach? How long do they take to reach it? How long do they take to reach it? Two ships are 10 km apart on a line running south to north. The one further north is streaming west at 20 km per hour. The other streaming north at 20 km per hour. Also, how long do they take to reach it? According to this problem or numerical problem given, small d equal 10 kilometer, that is the initial distance between the two ships, is 10 kilometer, and v1 is 10 kilometer per hour, 20 kilometer per hour. V2 is also 20 kilometer per hour due north, and v1 was 20 kilometer per hour due west. Now we have to find L min, or distance of closest approach of the two ships after the time t second. L min equal question mark and the time t equal question mark. The distance of closest approach is L min, and we have to find the expression of distance of closest approach. That is, we have to find the value of L min. Now we can draw the diagram. Here, this is north direction, and that is the first ship, and we can draw the second ship, and two ships were at a distance of 10 km from each other. In this case, we can draw the initial and final position of the two ships. The second ship is moving towards north with the velocity v2. This is the second ship which is moving towards north with the velocity v2, and that is the first ship, and the first ship will move with the velocity v1 towards west. First ship was at the point A, and the first ship is moving due west towards the point B with the velocity v1. At t equals 0 second, the second ship was at the point C, and at the instant t equal t second, the second ship reaches to the point K, and the first ship moves to the point B at the instant t equal t second. Distance, and in this case, the first ship is moving due west, and displacement of the first ship in time t second from the point A to B is x. X is the displacement of the first ship due west from the point A to B. And also we can denote the distance between the second ship at the final position and the first ship at the initial position. That this distance will be y. That distance will be y. Now we can denote the in this case, the first ship will be at the point B in its final position. First ship will be at the point B at instant t equal t second in its final position. Similarly, second ship will be at the point K at instant t equal t second in its final position. And we can denote the displacement of the first ship, that will be AB, and the displacement of the second ship will be CK. The initial distance between the two ships at the point A and C respectively is d, which is equal to 10 kilometer. D is equal to 10 kilometer, which is the initial distance between the first ship at the point A and the second ship at the point C. Initial distance between the two ships will be d, which is equal to AC. And what about the final distance between the two ships? AB and which one will be the final distance between the two ships, whether it is AB or AK or CK or AC or CB or KB. So final distance between the two ships will be which distance? It should be KB. KB is the final distance between the two ships at the point B and K at instant t equal t second. So final distance will be L, which will be equal to KB. Now the final distance between the two ships, the final distance between the two ships is given by L. That will be is given by KB, that is equal to root over AB square plus AK square, and that is L equal to root over in this case KB is L, so L will be equal to root over x square plus y square. L is equal to root over x square plus y square. Now x is equal to v1 into t, that is the displacement of the first ship from the point A to B with the velocity v1. X is equal to v1t, which is the displacement of the first ship. Also y equal to AC minus CK, that is y equal d minus v2t. Y is equal to d minus v2t, which is the distance of second ship in its final position. Y is the distance of second ship in its final position at the point K from the first ship in its initial position at the point A. From the first ship in its initial position at the point A. In its initial position at the point A. Y is the distance of second ship. Y is the distance of second ship in its final position at the point K from the first ship in its initial position at the point A. At the point A. So therefore y equal to d minus v2t, which is the distance of second ship in its final position at the point K from the first ship in its initial position at the point A. At the point A, and we get the expression of y as d minus v2t. Therefore, the distance of closest approach, or the distance of first ship in its final position to second ship in its final position is L, which is equal to root over x square plus y square, and we know that x is equal to v1t and y is equal to d minus v2t. And putting the expressions of x and y in the expression of L, we get root over v1t whole square plus under bracket d minus v2t, under bracket d minus v2t whole square, d minus v2t whole square. Therefore, L is equal to under bracket v1 square t square plus under bracket d minus v2t whole square whole to the power half. L is equal to under bracket v1 square t square plus d minus v2 whole square whole to the power half, or 1 by 2. And L is the distance between the two ships in their final positions, that is at the point B and K. L is the distance between the two ships at their final positions, that is at the point B and K. L is equal to v1 square t square plus d minus v2t whole square under bracket closed whole to the power half. That is the distance between the two ships at their final positions at the point B and K respectively. Now, if this distance, if the two ships are at the distance of closest approach, if the two ships are at the distance of closest approach, that is at the positions B and K, that is at the points B and K, In that case, the distance L will be minimum if the two ships are at the distance of closest approach. In that case, the distance L will be minimum. The distance L will be minimum. Here, L in the diagram. L is the distance between the two ships at their final positions, and this distance L will be minimum when the two ships are at the distance of closest approach. L is minimum if the two ships are at the distance of closest approach. If the two ships are at the distance of closest approach. As this distance L is minimum at the distance of closest approach, this L will be constant. That's why ddt of L will be 0. Differentiation of that distance L with respect to time will be 0. Or comma ddt, putting the expression of L, we get v1 square t square or v1 t under bracket whole square plus d minus v2 t whole square bracket close whole to the power half is equal 0. Or comma half under bracket v1t whole square plus under bracket d minus v2t whole square 1 by 2 minus 1 by 2 minus 1 ddt of multiplied by ddt of v1 square t square under bracket d minus v2t whole square will be equal to 0. Or comma 1 by 2 into 1 by 2 into v1t whole square plus d minus v2t whole square to the power minus 1 by 2 under bracket ddt of v1 square t square plus ddt of d minus v2t whole square bracket close equal 0. Or comma 1 divided by 2 square root v1t whole square plus under bracket d minus v2t whole square. Under bracket v1 square is brought outside ddt, that's why we get v1 square ddt of t square plus 2 into d minus v2t it multiplied by ddt of d minus v2t bracket closed equal 0. Or comma we can write v1 square into 2t plus 2 under bracket d minus v2t, and that will be ddt of d bracket close minus ddt of v2 is brought outside ddt, that's why minus v2 ddt of t bracket closed will be equal to 0, divided by 2 square root v1 square t whole square v1 t whole square plus d minus v2t whole square, that will be equal to 0. Or comma 2v1 square t plus 2 under bracket d minus v2t under bracket 0 because ddt of d is 0 into v2 minus v2 into 1. Now ddt of d is equal 0 because d is constant, and v2 into ddt of t becomes v2 into 1, and multiplying this denominator with 0 we get 0. So finally we get what? Or comma 2v1 square t minus 2v1 square t minus under bracket 2 d minus v2t into v2 equals 0. Or comma v1 square t minus under bracket d minus v2t into v2 equal 0. Now in the next line under bracket we can write as according to the question or numerical problem, v1 is equal to v2 is equal to 20 kilometer per hour. That means velocity of the first ship and second ship will be equal. That's why v1 can be taken common. v1 under bracket v1 into t minus d minus v2t under bracket is equal 0. Is equal 0. Here v2 is equal to v1, and considering this v2 as equal v1, we can take common v1 from v1 square and from the second term. So here we can write v1 under bracket v1t minus d minus v2t bracket close equal 0 equal 0, or comma v1t minus d minus v2t is equal 0. v1t minus under bracket d minus v2t, or comma v1t minus d plus v2t equals 0, or comma t is taken common under bracket v1 plus v2 into t minus d equals 0. That's why v1 plus v2 into t equal d. Therefore t is equal d divided by v1 plus v2. T is equal d divided by v1 plus v2. This is the time or instant of time at which two ships come at the distance of closest approach. T equal d divided by v1 plus v2, which is the instant of time at which the two ships come at the distance of closest approach. At the distance of closest approach. When the two ships are at the points A and K, at instant t equal t second, in that case the distance between the two ships is L. L is the distance between the two ships at the final positions, that is at the point A and K. Therefore, the time at which the two ships come at the distance of closest approach will be equal to d divided by v1 plus v2. Now d is equal to 10 kilometer, which was the initial distance between the two ships at their initial position, that is at the instant of time t equal 0 second. Now putting the values of d, v1 and v2, we get t equal 10 divided by 20 plus 20, where d is equal 10 kilometer, v1 equal 20 kilometer per hour due west, and v2 is also equal to 20 kilometer per hour due north. T is equal 10 divided by 20 plus 20, and t is the time at which two ships come at the distance of closest approach. Therefore t is equal to 1 by 4 hour. T is equal to 1 by 4 hour. This is the time at which two ships come at the distance of closest approach. That is, the two ships will be at the point A, B and K respectively at the instant t equal to 1 by 4 hour. Hence, the two ships will be at the distance of the closest approach. The two ships will be at the distance of closest approach at the instant of time 1 by 4 say hour at t equal 1 by 4 hour, that is at the 15 minutes, or after the 15 minutes two ships will be at the distance of closest approach, that is t is equal to 1 by 4 hour or 15 minutes. Now the distance of closest approach L mean is equal to root over v1t whole square plus under bracket d minus v2t whole square. Here L is the distance of closest approach between the two ships, and that is L min. L is the distance between the two ships at their final positions, equal root over, putting the values 20 into 1 by 4 bracket closed into whole square plus 10 minus 20 into 1 by 4 whole square, and we get square root 5 square plus 5 square, that is equal to 5 root 2, that is equal to 5 root 2, that is 5 into 1.414. Therefore L min is equal 7.07. L min is equal 7.07 kilometer. That is the distance of closest approach L is equal 7.07 kilometer. L is equal 7.07 kilometer, which is the distance of closest approach. Distance of closest approach between the two ships. Between the two ships. In this case, L is equal 7.07 kilometer, which is the distance of closest approach between the two ships after 1 by 4 hour. Now L is the distance of closest approach between the two ships at their final position, and this L or L is equal to 7.07 kilometer.